Hey guys, welcome back. So today's lesson, our episode, is all about the excitement known as mass percent and molarity. Our friend is back again. So those of you that were living in fear of doing calculations of molar mass, time to get out a calculator and probably a periodic table, something like that, because yeah, our friend the mole's back again for us today, so we're going to use him quite a bit. So in any case, trust me, if you get sad during your calculations, you can borrow Ben Molio here and you can snuggle him yourself. So here he is. Anyway, today we're going to talk about two different ways of representing concentration. Concentration of solutions specifically. So method number one, the 15d method, is called mass percent, and method number two, 15e, is called molarity. Between the two of them, if you have limited brain power, molarity is the one that you need. We use molarity all the time in chemistry class. Mass percent is more commonly used, say, at the grocery store, so not as important for us, but the molarity of the two, if you can only learn one, man. Molarity is the one that you need to use. So we're going to take a look at concentrations today and how do we quantify concentration. So here's you right now, right? Concentrating. So here's what I want you to do. Rank the images quickly from most concentrated to least concentrated. Which picture's dilute? Which picture's concentrated? No? Okay, so I'm kidding. The kid down here, this one up here is my favorite. That's me like every chem test, right? So anyway, this is not the kind of concentration we're talking about. All right, we're talking about concentration of solutions. We're looking at the ratios between solute and solvent. And more specifically, we're talking about solute and solution is really what we're talking about. But that idea of how much stuff is dissolved in a solution. And you guys know what concentration is. These are glasses of tea, by the way, up at the top. You guys know that if there is more solute dissolved, you're going to have a more concentrated solution. If you have less solute dissolved, you're going to have a dilute solution. So the T up on the top left there obviously is the most dilute, and then we have an entire range all the way to the most concentrated. So because the terms concentrated and dilute are sort of relative terms, we need to have a way of quantifying this. How do I know if one thing is more concentrated than another one? And I can't always do it just by looking at color. There's lots of clear solutions, there's dangerous solutions, you may not have a bunch of them around. So we need a way to quantify this. So there are two actual methods that we're going to use to quantify how concentrated a solution is. They're similar in some ways and they're slightly different in other ways, but there's two big methods. Method number one is called mass percent, and method number two is called molarity. Mass percent is based on masses, hence the name mass percent, and because it's a percent, it's still like a part divided by whole kind of thing times 100, just like every other percent that we've dealt with. Molarity is a little bit different. Molarity is based on the moles of solute. So that means that you have to convert it to our favorite unit, the mole, because what that does is it helps us take into account that atoms have different masses. So something can have, 5 grams of one substance and 5 grams of another substance can have very different numbers of particles in there. So that's why molarity is out there. So between the two of them, they have, like I said, slightly different uses. So I'm going to go into both of them in a little bit of detail here and do some example problems. So we'll kind of look at mass percent first, and then we'll do some molarity problems afterwards. So mass percent. Mass percent is, like I said, you'll see this at the grocery store quite a bit. If you walk around and look closely at labels, they'll say 70% like that isopropyl alcohol, 3% hydrogen peroxide, your different kinds of bleach, 6% versus 8%. Vinegar, for example, is another one. Regular vinegars, 5 to 8% vinegar versus cleaning vinegar. If you ever see that stuff, it's like 20%. You definitely do not want to put cleaning vinegar on your salad. It would burn your mouth. Not a lot of fun. But it does help clean your windows because it's got a lot more of that reactive stuff in there. It's more concentrated. So with these two things, it's based on masses. And this makes it a little bit easier to understand, just sort of in a general sense, that the bigger the percent, obviously the more concentrated it is, duh. And the smaller percent, the more diluted it is, the more water that's present. So like I said, it's pretty easy to understand. It's also easier if you're doing massive preparations of things. Sometimes just doing like huge industrial quantities can be easier to do just based on mass. I need 500 kilos of this and 2,000 kilos of that. So that's why mass percent is out there. So doing mass percent problems actually isn't very difficult as long as you keep in mind some basic ideas. So number one, it's percent. So you're always doing part divided by whole. And the trick here is that we need to do the mass of the solute. That's the important part that we deal with. And then you have to have the mass of the whole. The mass of the whole is the solution, though, not just the mass of the solvent. It's got to be mass of solution, the whole thing on the bottom. So there's a few little trick, wrinkly kind of questions that we'll throw in there that may have you ask that. You'll always multiply by 100 to get to a percent. And otherwise you'll end up with, a 0.25 or something like that as an answer. You got to multiply by 100 to get to your mass percent. Keep in mind that I will ask you to be able to do algebraic rearrangements. So given any two of these three, you should be able to solve for the other one. It's not just if I give you this one and this one, can you divide? But what if I give you mass percent and the mass of the solution? Can you calculate the mass of the solute? Or if I give you mass percent and the mass of the solute, could you calculate the mass of the solution? So that's what I mean by algebraic rearrangement. So don't forget to brush up on your basic algebra skills. So here's a couple of example problems that we're going to take a look at. I put the formula up at the top, so you've got it right there in front of you. Your best bet here, if you want to watch this one, that's fine, but get a calculator out. Actually, there's two problems on here. Get a calculator out. See if you can scratch this out on a piece of paper. These aren't too challenging, but we'll take a look at it. So over here we've got acetic acid. Is this with the lovely jar? It's actually the same stuff that vinegar is made of, and I guarantee if you put that acetic acid on your salad, it would probably melt your salad. It's terribly unpleasant. It's the fumes are so strong that you have to do it in a fume hood. It makes you leave the room. It's not just vinegar. It's like extreme vinegar. So question number one's up at the top. What's the mass percent of a solution containing 37 grams of acetic acid and 125 grams of water? And then there's a second problem down here. How many grams of acetic acid are needed to make 55 grams of an 8.7% vinegar solution? Both of these are going to use our mass percent equation. So let's take a look at this top one. So I've got up here, it's important to go through your idea of thinking, what do these numbers mean? This 37 grams of acetic acid, is that mass percent, mass of solute, or mass of solution? So this particular case, this acetic acid has got to be my solute, because I'm making a solution with that. So this would be the number that goes on the top of my equation. And there's 125 grams of water. Is this mass of solute, mass of solution, or mass percent? Well, it's not mass percent. It's one of the two masses. It's not mass of solute because it's water. And it's really not mass of solution either. This is one of those little trick questions here. The mass of our solution has to be the combined masses of our solvent, which is the water, and our solute, which is the acetic acid. So our combined mass is a little bit more than you'd think. It's not just 125 on the bottom. So here's what this looks like. I've got my little mass percent formula right here. So mass percent is equal to the mass of the solute up on top, divided by the total mass of the solution. So you can see what I've done here is I've added the two components together. Again, it's a mixture. You have to have the solute and the solvent in there together to get the total mass of solution, and then you multiply by 100 to turn it into a percent. So when you calculate it out, you get 22.8395, and then I'll remind you, you have to do sig figs. We've got 2 sig figs in our problem. This one has 3 sig figs, I know, but our least number in our problem is 2, so it means I rounded our answer to 2 sig figs. If I had it in 3 sig figs, I'd have to write it as 22.8. If I had it in 4 sig figs, I'd have to write it as 22.84. So keep in mind, you have to do double check that. You'll lose little half-point errors on your math if you don't check that last piece. So there you go. Mass of the solute divided by the total mass of the solution. Okay, let's take a look at the bottom one. Grams of acetic acid needed to make 550 grams of an 8.7% vinegar solution. So this 550 grams, is it mass percent, mass of solute, or mass of solution? If you kind of read between the lines here, this 550 grams is my solution. It's the total mass at the end that I need to make. This 8.7% here is my mass percent, so that's going to go on the left side of my equation. So when we plug it in, it kind of looks like this one up here at the top. Always start with your basics. I plug in my 8.7 on the left because it's my mass percent. I don't know how many grams I've got, so I'm going to put that as my X on the top. And then on the bottom here is my 550 because that's my total mass of my solution. And there's my times 100. So in the next step here, all I did was move the 100 over. I divided by 100 to get this down to its decimal place version, 0.087 equals x over 550. And then I did the algebra math, multiplied by 550, multiplied this side by 550 to get those to cancel out, and I get this as my final answer. X equals 47.85, and this would be in grams. So the last part is, again, double check your sig figs. Again, this problem only has 2 sig figs. Actually, both of these numbers only have 2 sig figs. So I rounded this to exactly 48 grams. So there's how I got the final answer for that particular problem. So when I'm trying to do molarity of a solution is a whole different kind of thing. You'll have to wait.
Okay.
I'm sorry.
That's fine.
Give me like 10 minutes.
Okay.
One of my students is coming in asking for help. What is she thinking?
I'm
Craziness.
sorry. I don't want to fail.
I don't want to fail either. So anyway, moving along, we've got molarity of a solution. Our second method, so those were mass percent. This is molarity. So we're going to take a look at the more chemistry way to calculate the concentration of a solution, which is when we're dealing with our friend the mole. We have to use moles for this because remember, moles is how we deal with the concept of kind of dealing with the different masses of different atoms. So an atom of hydrogen weighs way less than an atom of lead or something along those lines. So we can't just say 5 grams has a certain amount to it. When we standardize by using moles, it gives us a much better idea of how many reactive particles are actually present in our solution. So here's the equation. Molarity is defined as moles of solute divided by volume of solution. So the way I typically write it is this. I usually write it as molarity, which is this funny looking capital italic M, is moles per liter. And that's how I tend to write it. It makes it a little bit easier for me to remember. Yes, your volume has to be in liters. So number one, we need to have moles of solute, and the trick will be you can't have it in grams. So we have to do molar mass conversions to get it into moles first. And again, why do we use moles? Because it helps us standardize out for these different numbers, different masses of atoms that are out there. So we can kind of get to a consistent idea of how many reactive things are there, regardless of whether they're light like hydrogen or heavy like gold or lead or something like that. Second thing you've got to get is the bottom of this equation is volume of solution. Again, remember it's the volume of the total solution, not the volume of the solvent, and it does have to be in liters. So a lot of times you're given milliliters because it's commonly used small volumes. So all you have to do to convert from milliliters to liters is divide by 1,000. Again, there's 1,000 milliliters equals 1 liter. So, and again, last thing but not least, you will have to be able to do algebraic rearrangements of this, just like the other one where I'll give you any two of the three, and you should be able to calculate for the third. So let's take a look at an example problem of what this is. So here's an example problem number one. What's the molarity of 225 milliliter solution created from 34.6 grams of magnesium chloride? And the formula for magnesium chloride is MgCl2. So here's our little equation up here that I write down all the time. Molarity equals moles per liter. So let's take a look. This 225. This is 225 milliliters of solution. So this is going to end up being on the bottom of our equation. This is kind of the per liters part. But there's a problem with our units. It's in milliliters, so we'll have to fix that. And then this thing over here, the 34.6 grams of magnesium chloride, that's our solute. But it's in grams, so we're going to have to convert it to moles. So again, here's how I kind of do my pre-work. To do my equation, I'm always going to have moles per liter. Grams is going to get converted to be on the top. Milliliters is going to get converted to be on the bottom. So here's my two little problems that kind of take care of that math for me. Here's the grams to moles part. So 34.6 grams of magnesium chloride was given to me in the problem. This number over here is molar mass. I looked at the periodic table, found the mass of 1 magnesium, I added it to the mass of 2 chlorines. Remember, we're always using 2 decimal places when we're doing molar masses of things from the periodic table, so that's where that 95.21 comes from. And then I just divide them out. So I get this as an answer. Here it is in sig figs. We've got 3 sig figs in our problem. 0.363 moles of magnesium chloride are present. Second thing is my little conversion to get from milliliters to liters. I'm doing this bottom part right now. So 225 milliliters, divide by 1,000. Basically, you're just moving the decimal place over 3 places. You don't have to show me this every single time once you get used to it. You're just moving the decimal place. So there it is, 0.225 liters. So now I can use my molarity equation directly. So this is what it looks like when I put that in there. So it's moles per liter. Moles on the top cannot be grams. Liters is on the bottom, cannot be milliliters. You have to do that pre-work. And then I just divide it out. It's 1.61 molarity, or moles per liter, is the unit for this. So you can either say this as 1.61 molar, would be a correct way to pronounce that. The units, you can just write it as that big funky M. That's totally acceptable. Or you can write it as 1.61 moles per liter. It's sort of understood that when you see this big molar, it means moles per liter. So you can say it either way, whichever makes you happy. Just find a method and stick with it. Here's our second problem, a little bit tougher in some ways. How would you prepare 375 milliliters of a 1.25 molar sodium nitrate solution? So again, let's look at our formula. We've got molarity is moles per liter. So what do we have in our problem here? I've got this thing, 1.25 molar. It's going to go here on the left. And then I've got this 375 milliliters of that solution. That's going to go down here. That's my volume. So let's take a look at what this looks like when we work it all out. Again, here's my kind of some of my pre-work what's here. I'm given that its molarity is 1.25. I'm given that the volume of it's 375. I'm going to have to convert that to liters. So there it is. And then the last thing I'm going to need here is because I'm going to be given moles, I do need to know what my formula is. So yeah, you're going to have to go back and kind of review your names and formulas and your polyatomics and that kind of stuff. Here's the formula for sodium nitrate. Sodium is Na with a 1 plus charge. Nitrate's a polyatomic, NO3, there it is with a 1 minus charge. So there's our correct formula. They are balanced out like that. The reason why I need to do that is because I'm going to get a funky answer here that I'm going to have to convert. You'll see where it goes. So here's my math. I plug my numbers in. I've got my 0.125 molar on the left spot. I've got my volume in liters on the bottom spot, and then I'm just going to do the algebra to solve for moles. So here's my answer here. There it is. 0.469 moles of sodium nitrate are required. Now, that's nice, and that's wonderful. I've got the right number of sig figs, but it's not done yet. And here's one of the hidden kind of problems in these. I don't know about you, but if I asked you guys to go over and get me 0.469 moles of sodium nitrate, and I just handed you a jar of sodium nitrate, you'd all look at me like, how do I do that? Because if I go use a scale, the scale is in the unit of grams. There's no such thing as a molar scale. So even though it kind of looks like you're done, you have to do one more step here. If it asks you how to prepare it, that means I need an answer in grams, because there is no way to go over to a scale and just go, weigh out 0.4 moles of it or 0.5 moles of this as it is. So you have to do that last step. So that last step is where we start to use molar mass, and that's why I need the formula. So here it is. The molar mass of sodium nitrate is 85 grams per mole. Oops, sorry about that. Let me go back. It's 85 grams per mole, like that, and I get that from sodium's 23, nitrogen's 14, oxygen is 16 times 3. That's where that number came from. That's periodic table numbers right there. And then when I multiply it out, I get that number. So that means I need 39.9 grams of sodium nitrate. So how I would prepare that? I would measure up my 39.9 grams of sodium nitrate. I'd splash it in some water, dissolve it all, and I'd bring the water volume up to exactly 375 milliliters. And that would make a perfect 1.25 molar solution. So there you go, dealing with our different types of solutions today and concentrations of solutions. So just by way of review, remember that concentration is simply a ratio of solute to solvent. We can talk about it in a relative way, like it's dilute or concentrated, but typically it's more important for us to deal with it in a quantitative way. So the consumer way of dealing with it quantitatively is called mass percent, which is just mass divided by mass. Mass of the solute divided by the mass of the solution times 100. And again, that's in grams, and then by the time you divide it out, you get a percent as your final answer. 85%, 25%, 100%, something like that. Can't have a 100% solution, except water. Okay, so molarity is the other thing that you could do, and this is what we do in chemistry all the time. So again, if you have limited brain power, this is the part to focus on. Molarity is standardized based on molar masses. So with this, our units is moles per liter. Molarity is moles per liter. It's kind of a weird unit. You'll get used to it. You do need to do molar mass conversions for this, which is, again, using periodic tables. And then you have to do that final division where you do the moles of the solute divided by the liters of solution. So you might have to convert from milliliters to liters. So there you go, dealing with concentrations and moles. You knew it was coming back. There you go. Have a good weekend, or I hope you had a good weekend. You're probably watching this on a Sunday, right? I know how you are. See you in class tomorrow.